record. Usually when I talk, I occupy most of the screen. So it's not that I want to occupy most of the screen. What I want to do is see the whiteboard so I can tell if you can see it.
We can see it from here.
Okay, so I think on one of the videos I was talking off the bottom of the screen and I said words like, and you can see, and said, no, you couldn't really see. So if I talking about something that's off the screen, then interrupt me, okay?
Will do.
I just have this little thumb sketch. For some reason, it's not making me big. So we're recording now. So real quickly, the review, the exam. I think on Wednesday, the format will be just like all the other, well, as much as we can. That is, there will be problems for you to work. You need to show your work. There will be no calculator allowed, and I guess you're on the honor system there. You can bring a 3x5 note card. You cannot consult the internet. And again, you know, maybe you're on the honor system there, but the format is just like all of the others. You want to show your work so that if your answer's wrong, you know, I can track down the nature of the mistake and award points accordingly. Most of the problems, I think, will be like homework problems, maybe not every single one. Hopefully I can give you a chance to be creative and take what we've learned and solve a situation we've never seen before on the homework. But that's a pretty small part of the exam. Most of it are just going to be like homework problems. And right after exam 2, we spent one day talking about applications of differential equations. Remember, we did Newton's law of cooling, I think. That is not going to be on the exam. So the exam is going to consist only of chapters 10 and 11, the work that we've done there. And in fact, the lecture I posted on Friday, differentiating and integrating power series, that's not going to be on the exam either because we really haven't had any good homework over that material yet. So all of chapter 10 plus section 2 of chapter 11. We didn't do section 1 of chapter 11. We'll do it when we do section 3. For some reason, I don't quite understand the author's motivation, but section 1 and 3 are related, and then section 2 is in the middle. So that'll be what we start on Friday after the exam. Sections 1 and 3, we'll put them together. So to just quickly list out those topics that are eligible for the exam on Wednesday, I posted a video reviewing all of the tests. And if you watch that video, then you remember we've come up with 10 ways to decide the behavior of a series. You know, that gives us a lot of power, but also gives us a lot of responsibility, I guess, to know like which of the 10 is going to do the job for us. If we only had one way to do it, then every problem we'd know exactly what to do. Now we have 10 ways, and so we have to think a little bit about, you know, what test might be the right one. And I can give you some guidelines about that in a minute, but I encourage you to watch that video. And at the end of it, I picked 4 sort of random problems out of the book. They weren't random in that I wanted to use 4 different tests. I didn't want to use the same test 4 times. And so we did some there, and maybe I'll do a couple more at the end of this video. We'll see. So that'll probably be 70% at least of the exam, just showing me that you can use those tests. Actually, 7 of them are tests. This is explained in the video. 2 of them are specific kinds of series, geometric and P-series. And, you know, we could probably call it the P-series test. You know, a P-series converges if and only if P is bigger than 1, but it's not really labeled a test. And the 10th one, then 7 tests, 2 specific series. And then the 10th one is just the very definition, the limit of the sequence of partial sums, which we did twice, and basically we're done working with it as far as analyzing the behavior of a series. We've gotten all the information out of it we can. It's too difficult to use, except in the two cases we did do, and that was the telescoping partial sum, and then of course the very important geometric series. So what that video doesn't cover is the very first section of chapter 10, which is sequences. So don't be surprised if you're just given a sequence on the exam that has no connection to a series whatsoever, and maybe I'll ask questions about it, like, is there a limit? Is it increasing? Is it bounded? Those things we talked about, remember, early in chapter 10. So hopefully you can see it on the board, the first thing on the list there. And then the video from Friday or Wednesday, I forget, infinite series. I think it's the series at the top of the panel for last week. And take a look at that. And then on chapter 11, there are two things that we've talked about that could be on the exam. I would say will be on the exam. The first thing is the very nature of what a power series is. And let me just write it out here symbolically. So we have a sub k, x to the k. And k starts somewhere, it doesn't really matter. Let's start it at 1, and it goes to infinity. So in chapter 10, all of our series were specific series. Like here it is, does it converge or diverge? And now we have these series that are a function of x. So, and we changed the question from does it converge or diverge in chapter 10. In chapter 11, we're asking the question, for what values of x does it converge? Okay, and the good news is we could use the test we learned there to help us decide the issue. And we discovered there's some, form to the answer. There's this thing called the radius of convergence. And remember, there are 3 possibilities. It converges for every number inside the interval minus r to r. It diverges for every number outside that interval, and it may or may not converge at the endpoints. We just have to investigate individually those endpoints and see what's going on there using what we learned from chapter 10. When, once we plug the endpoints in, now we've reduced it to a chapter 10 problem. So hopefully we can use what we learned there. And that's pretty much it. So there are 2 other cases here. One is that it only converges at 0, which means it's just a number. It's not a series. And then the other possibility is that it converges for all x, in which case we would say the radius was infinity. And the interval, of course, if it converges for all, there is no issue at the endpoints. It would just be minus infinity to plus infinity. If you get it converge at 0, to have anything interesting, I guess we would need this to start at 0. So we have one term with no x's on it. But that's a totally boring, it's not an infinite series. Mostly we're looking at cases where r is a positive number or perhaps infinity. All right, when we had our normal exams, or exams when class was normal, Nate, you've had, I think, 6 exams from me. Kate, this is only your 3rd. But you know that the day before exams, this is what I do. I outline the topics, and then I check and see if there are any questions. Let me do just a couple of problems here. We'll get them on the recording, and again, I'll pick them sort of semi-randomly. Let's start with chapter 11. Do you have any questions for me first?
Actually, I have to leave here in a few minutes, but would you be able to review or do an example of the sequence problem real quick? Because you said I don't think you touched on it in the video. I haven't had a chance to watch it yet, but that's probably the one thing.
So in a sense, all of the tests that involve limits, the limit comparison, the ratio test, the root test, sort of the integral test, we take the limit of on an integral, right? Those are all kind of taking limits of sequences, but to get one totally, here's one, number 55 on page 659. Can you see this panel over here?
Yeah.
Okie doke. So here is a sequence. -1 to the n over 2 to the n. So like I said, there's no series here. This is just the sequence. We reviewed or learned about sequences in section 1 because everything we've said about understanding infinite series involves sequences. So we just did sequences to get us started, and then as soon as we were comfortable, we moved on to series. And so the question you might ask here is, let me just make up some questions. Is this sequence increasing or decreasing? And does it have a limit? If so, what? What do you think about the first question?
I'd say it's decreasing.
Okay. Let's write out a few terms. I didn't actually say, let's say it starts at n equals 1, then goes to infinity. N equals 1, I believe we get -1/2. Is that right?
Yes.
And what do you get when n equals 2?
Positive 1/4.
1/4. And how about n equals 3?
Negative 1/8.
Yeah, and can you tell me the next one without calculating? Without looking at that formula?
Positive 1/16.
Yeah. So now, Nate, what do you think? Increasing or decreasing?
Decreasing. Or, well, sorry, increasing.
Kate?
Well, it's oscillating, but eventually it's going to 0.
Yeah. So the answer here is 0, but it is neither increasing nor decreasing. Nate, you see?
Mm-hmm.
Bouncing
Because
around.
it goes from positives and negative.
+1/4, -1/8, +1/16. So it's neither increasing nor decreasing, but it does have a limit. The limit is 0. How about this one? Let's do another one. Number 66. This time we'll just ask about the limit. Sine of n, 66. Sine of 6n over 5n. And let's say n starts at 1 and goes to infinity. What do you think? So I don't have to write the whole thing. Let's call that formula a sub n. And then we'll take the limit as n goes to infinity. What do you think? So what does sine 6n do? It oscillates back and forth between -1 and 1, right? So as n increases, this thing, the numerator bounces back and forth, but what's the denominator? It's going to infinity, which means sine n over 6n is going to 0. So it's like we have a sine wave trapped in between 1 over n and -1 over n. You see that?
Yeah.
So what's the limit?
0.
0. Yeah. Now it's purely coincidence that I picked 2 examples that oscillate. Like, don't think, oh man, it's going to be, I mean, I just picked 2 at random. Hopefully 2 that would be halfway interesting. Here's an interesting one. Any questions?
Nope.
So very different. And let's see, this is recorded so I can erase it. I believe it's number 68. So the sequence is the integral from 1 to n x to the -2 dx. Yeah, pretty weird looking, right? But we know how to evaluate that integral. So let's do it. Raise the power. Divide by the new power. 1 to n. I'm going to pull this minus out. And I get 1 over n minus 1. You see that? Any questions there?
Where'd the -1 come from?
Right here?
Well, no. For the next part, you have 1 over n minus 1.
Pull the minus sign out. And because the number's 1, all it does is change the sign. If it was a 2, then I'd need to have a 1/2 there, right? But all it does is change the sign.
Yeah, you had x over -1, but now you have 1 over n minus 1. Where'd that extra -1 come from?
Oh, okay. We're evaluating an integral, so we plug in the upper limit.
Oh, okay. I got you. You already did that step. I got you. You moved on. Got you.
Yeah. Okay. So this is a weird way, it's a way to confuse students maybe, way to write this formula, 1 minus 1 over n. So this sequence right here is the same as this one. You see that? And what's the limit?
1.
1. 1 over n goes to 0. Yeah, so when you look at this, it looks like really weird, but we don't panic. We know how to evaluate this integral. We do it, and then we get this super nice sequence whose limit is, can I say, obvious? Okay. So that's your question about sequences, and I don't, Nate, I don't anticipate getting really more elaborate than these examples. All 3 of these I picked out from page 659. You know, there are more complicated limits, but maybe none more complicated for, you know, the typical Calc 2 student than the one we just did. It looks so weird. You know, there might be a little bit of panic to figure out. But anyway, you could take a look at some of those there.
Sweet. Thanks for your help. I'm going to run to my physics class now, so
All right,
I'll look
thanks.
for your email later today.
Okie doke.
All right. Talk to you Wednesday.
All right. So Kate, you have like a personal tutoring session now.
Yes. I did have one question.
Sweet.
So it was on the last homework assignment.
Which
And the question essentially boils down to, when do you know the radius of convergence is 0? And that
you're asking about number.
it was the first one on the homework.
Now, there were only 2, right?
Yeah.
Yeah, I didn't look ahead very well. There's the information I presented in that video is stuff I really like, and I wish there were better homework problems over it. But the authors and I guess, sort of disagree on what we think is fun. I teach a course in probability where those things that we did, differentiating and integrating, we have to do them there, and maybe that's why I like the technique. But I gave this, I don't know, involved lecture, and then I really couldn't get any homework over it. So let's do number 11. And actually, when I assign number, well, it's number 11 in the book. It's number 1 on the assignment. Actually, when I signed it, I thought it was something different.
Oh, okay.
But, you know, I worked it out, and then I discovered it's not. So what do we have? The summation, it starts somewhere, doesn't matter where.
Yeah, I don't even think it didn't put anything.
Yeah, so kx to the k, right?
Yeah, mine was 15k to the times 15, but it doesn't really matter.
So you agree it doesn't really matter.
Yeah.
All right. So how did you do it?
I did the root test.
Okay, yeah, the root or the ratio.
Yeah.
I don't think that we will ever, on a power series, okay, well, there's always an exception. Some of the power series are actually geometric series. And if you see, I can give you an example of one, and maybe I assigned one. I think I did, just because a lot of them in the book are geometric series. And it's hard to make a good assignment without hitting a few of them. But normally, so let's say there are 3 things we'll do for a power series. We'll do the ratio, or maybe we'll do the root, or maybe we'll be lucky enough that it's just a geometric. And it is geometric and you don't notice it, you can still use the ratio test. So it's like you don't really have to know that, the ratio or the root. So let's try the root test. We'll take the limit as k goes to infinity. Kth root, you can see that the root test is a super good option here because the whole formula is raised to the kth power. And we get the limit as k goes to infinity. Kx, right?
Yes.
What's that limit?
Infinity.
Yeah. So is the ratio test. That's bigger than 1. I'm sorry, it's the root test. So it diverges and it doesn't depend on x. So that means r is 0.
Okay. So pretty much if you had gotten even like 2 or 3, would r still be 0? Like for your limit?
If you would have gotten 2 and it did not, and that's it, not 2x?
Yeah.
Yeah, yes.
Okay. So anything bigger than 1, your radius is 0.
What typically happens, the way we think about it is the limit we get here depends upon x, and then we, solve the inequality, that thing less than 1. But this, when it doesn't depend on x, if this is less than 1, it converges for all x. If it's bigger than 1, it diverges for all x.
Okay.
Except the trivial case, and actually, I think this one does start at 1. So it actually, well, it does converge if x equals 0. It's totally trivial, totally boring.
Yeah, because the whole thing's 0. So, okay, that makes sense.
Anything else?
I think that's pretty much it. Yeah, I just found there was some on the Pearson assignment where like I would go to use a different test than they had used, and so, but I wasn't quite getting the answer, so then I would have to just scratch my whole method in order to use the example they provide.
Yeah, I think, I don't know if I recorded and posted, but on one of the very first Zoom sessions I had, I think I may have picked a series randomly, and I suggested a comparison. And we worked through it. There were a few students. I don't know, were you that? You might have been there that day.
I think I was there that day.
Yeah, and I picked the wrong series. I think you were there because it was the only day I've had more than 2 people in the room at the same time. So now that's probably good of me to model that. It's like, I mean, sometimes you don't know. And some of them are simple, straightforward. If you don't mind, oh, we have a new person. We have oh, how soon I forget. Mark. Welcome.
Hello.
So we're reviewing for the exam on Wednesday, and I'm recording this session and the details are on it. I'll not repeat them. I'll give you a chance to ask questions, but as far as the details, both the details about how to take the exam, not fully developed yet, but where I'm at is outlined previously on this video. And then the topics are also, like I normally do, you've had several exams from me, and I list the topics out before the exam, and they're all there. And now we had Kate and Nate here earlier, and we're just kind of answering their questions. So given that you can watch this video to get kind of big details about the exam, do you have any specific questions that maybe Kate might benefit from as well?
Yeah, I had this one problem that I found in the book that I was trying to figure out what tests to use on it, but I couldn't quite figure it out.
Tell me it.
All right, it was the sum as k goes from 3 to infinity, the natural log of x over, or no, sorry, the natural log of k over k to the 3/2 power.
You just kind of pick this randomly.
It looked like one that I didn't know how to solve, so I figured I'd learn a lot from it.
Yeah. So let me tell you a little story about this very series. I've been teaching Calc 2 for a long time. And you know, maybe a guy can convince himself that he knows it all and you know, there's nothing new to learn. I mean, that's not true at all, but anyway, I would, just for the fun of it, I was looking through the series in the book and wondering, like, is there a good challenge in there for me? Just, you know, for the fun of it. And I picked this very series. So maybe that makes you feel good. I mean, it's not obvious. You picked a good one. And so what do you think it does? Does it converge or diverge? Do you have a gut feeling? You
Well,
don't-
my first thought was, since it's a P series and the power in this case is greater than 1, I assumed at first it would converge. I'm not sure about the natural log of x though, but I do know that it gets a little bit smaller as it continues, but I don't know if that's enough for it to.
Yeah, so let me correct something that you said. You said this is a P series and it's not.
Well, it looks like a P series is what I meant to say.
Yeah, so P series can't have a log in the numerator. They can't have a log anywhere. P series are really wonderful when we have them, but you know, they can get messed up pretty easily. But you're right in thinking that, well, it's like a P series. And if I say it's like something, that suggests that maybe what I'm going to do is use the comparison test. And if the log weren't there, it would absolutely converge. I think you said it, because P is 3/2, it's bigger than 1. And you also said the log, it does go to infinity, but it's not in a big hurry. Which do you think goes to infinity faster, the log of K or the square root of K?
I'm going to go with square root.
You're right. Yeah. In fact, K to any positive power is going to beat the log. The log is super slow. It does go to infinity, but it just plods along. So it's like, if you think of it as a P series, it's like we have this, we have a half of a unit kind of surplus, right? Because we have 3/2 power and it only needs to be bigger than 1. So it's like I have a half of a unit there, but I have to overcome the log. So it may be the first thing to try, and tell me if you tried this, is, and I'll say in advance, unlike the other day, a week or so ago, I don't think this is going to settle the issue, but it's a reasonable thing to try. And so let's give it a try. And if it doesn't settle it, then we'll see if we can tweak it. Okay? Does that seem like a reasonable way to go?
Yep, sounds good to me.
Yeah, so we're going to compare to, actually, I'll let you pick. Or should we just go with that one? Like, just take the P series. Okay? Does that seem like a reasonable way to go? So let's try it. I'm going to calculate the limit. The series we know, we write on the bottom. The series we don't know, we write on the top. And right away, those K to the 3/2 cancel. And we get infinity. Right?
Yeah.
Now, it's possible that infinity can settle the issue. Let's turn back to the This is a detail you definitely would want on your 3x5 note card. Those second and third cases of the limit comparison test. On page 685. So, if we make like the perfect choice, most of the time we're going to get a limit that's positive and finite. That is the first case. We'll settle it. And Jenny Duran is joining us. Can you hear me?
Yes.
Sweet, I can hear you too. We're working on the problem on the board, which is out of the book. We haven't identified which number it is, but you can see it on the board, and it doesn't really matter which number it is. Jenny, I'm recording this session, so you can go back and watch it from the beginning and get the full context. All right, so we applied the limit comparison. We got infinity, and now I looked the third case of the limit comparison, page 685 says if you get infinity and the series you chose, the BKs they call it there, if it diverges, then we've settled the issue. Well, the series we chose is this one. Does it converge or diverge?
Converges.
Yeah, so we failed. This series is not going to settle the issue. Okay, so fail with a sad face. But we're not discouraged. Yeah, if it were exam, then we'd panic because the clock is ticking and we got to start all over. But we're not having an exam, we're just solving problems. So we gave it a good shot and it didn't work, so we're just going to come back. Kate, you play basketball, everything's not always works the first time, right? You got to work at it, and that makes it fun. If everything was easy all the time, there would be no sense of accomplishment. And so this example will give us a good sense of accomplishment. I think we're going to be able to resolve it. But we do have to start over, and I don't see a better test. I mean, we could talk about the others, maybe the integral test. Well, the function ln x over x to the 3/2, I don't see a good antiderivative there. Like, that's a non-starter, I think. The ratio test will get us 1. I'm guaranteed of it, and that means it's going to fail. And so I think we just have to go back, stick with the limit comparison, but let's make a better choice. So like I talked about before, that extra half power we have, the 3/2, all we need is something bigger than 1. It can overcome the log k, but k to the 3/2 didn't work. So what I'm going to do is pick a power on k that it still converges, but it's less than 3/2 power. Okay, and I think there are a lot of powers that will work here. I want it to be bigger than 1, but less than 3/2. I want it to be bigger than 1 so it converges. We believe this converges, but I want it to be less than 3/2 because 3/2 obviously didn't work. So what's a number between 1 and 3/2? Mark, just pick a number.
I guess you could do 1 and 5/4.
5/4. Yeah, split the difference. So this time we're going to, actually I'm going to erase this, most of it. We're going to compare to 1 over k to the 5/4, which converges, for the record, because 5/4 is bigger than 1. And now we're going to take the limit as k goes to infinity. The series we know on the bottom, the series we don't know on the top. The reason we do it that way every time is so if we run into cases 2 and 3, we have a chance of resolving the issue. That is, to use cases 2 and 3, we have to put the series we know on the bottom. All right, and then they don't cancel. We have a little bit of work to do. I'm going to have k to the 5/4 times ln k divided by k to the 3/2. Are you with me? Can you see it okay?
Yeah, I can see it.
Yes.
Okay. Now, if I cancel this 5/4 of a power into this 3/2, how much is left down below? So 3/2 minus 5/4. Well, 3/2 is 6/4, right? And so if we cancel
7/4.
1/4, yeah. Questions? Kate?
Nope, we're good.
Sweet. Do we know this limit? Or is there, do we know how to find it? You want to try
Say
this?
that didn't you say that any positive exponent goes to infinity faster than the natural log?
Yes.
So it would be 0.
So it would be 0. Yeah. Now, if this problem were on the exam, Kate, maybe you would be a little bit nervous about saying that. It's not like theorem 10.5, you know. And so if you needed to, you could use L'Hopital's rule. Well, let's do it. Any questions, Jenny or Mark?
No, I think I'm good.
Yeah, the log goes to infinity. The k to any positive power goes to infinity, so we can use L'Hopital. And the one wonderful thing about L'Hopital is it gets rid of that log, right? So the derivative ln k is 1 over k, and then down here we have kind of the nasty looking thing, 1/4 k to the minus 3/4. Take a 4 out. And it looks like we get 1 over k to the 1/4, which goes to 0. Yep. And now back to the comparison test that I say page 785. This time we got 0. That's the middle clause. And the series we pick converges. Does it converge? It does. We made it clear up front. So this one converges by part C of the limit comparison. So Mark, you spotted a super good one. Actually, we could use any power between 1 and 1.5. I think I told you I looked at this problem earlier. I think I choose 7/6. Don't ask me why. But I think 5/4 is a much better choice, although it's sort of the same either way. Okay, Mark, does that make you feel good that you found a hard one that stumped you a little bit?
Yeah, it was cool. We got to the end. And is it any coincidence that k to the 1/4 is exactly the difference between the number I chose and 1?
Between 1 and 3/2?
Well, no, so I chose 5/4,
For here.
which had to be greater than 1, and it happens that the power in the very end is to the 1/4, which is the difference between 5/4 and 1.
Yes, that's not a coincidence. If you mean in the very end, in this limit, right there.
Yeah, that's correct.
Yeah, I think you need to pick a power between 1 and 1.5. I think if you pick one bigger than 1.5, we're going to run into case 2 or 3, but it's not going to settle the issue. But any number between 1 and 1.5 ought to do the job. Let's give Jenny a chance. Do you have any particular problems, Jenny, that you would like to ask a question about, thinking of the exam on Wednesday?
Sorry, I was muted. So I had a question, yes, on one of the problems we have for the homework, and I did one method, and I thought it should work, and I got a number, but that kind of worked, but I got a different number then, and then I tried to do the ratio, and then I got it right. So I just was wondering why the other couldn't work, and why did I got a different.
So which problem is it?
It was the 7 ones from like 2, not this last homework, the one before.
Oh, the 7th one on the assignment?
Yeah, it was 10.8 number.
Oh, 10.8.
When they say k to the 21 over 21 over k to the k.
Mark? So we'll work on your problem, Jenny. I just noticed something. Mark, you ought to take a look at number 7, not now, later, number 71 from section 8. It's real similar to one we just did. So later, take a look at it. So Jenny, can you tell me the number in the book?
I can look it up.
Look it up. Yeah. Did I hear a baby crying?
Yeah.
She probably couldn't get that problem figured out. It's crying.
It was just, I think, wasn't it just k to some number and then that same over that same number to the k?
Yeah.
Oh, okay. A lot of K's going on here. With a K, K to some number, how about 5? Divided by 5 to the K?
Yeah. I had 21, but it's the same thing.
I'm easy. And it doesn't matter where it starts.
Yeah, 1 to infinity, but
Yeah, we can start it at 0. We're not finding the sum, so that doesn't matter. Now, tell me again what you said, Jenny.
well, I wanted to use the geometric series.
Ah. This is not a geometric series. How come?
Can I know why?
Can you know why?
Yes, because I thought I can have r to the n.
Yeah, so if you cover up the numerator,
Mhm.
it's a geometric series. Like if you replace the numerator with any constant. But remember, a geometric series is, maybe some number, call it a times r to the power k. The only way that the index variable k shows up is in the exponent.
Oh, I see it now. Okay.
Yeah, and that's what we have here. Wonderful, but it's not what we have here. K is not in the exponent slot, so it's not geometric. Unfortunately.
Got it. And what would you use? I guess the ratio would be a good one.
So
I had this I had another problem that it said 9 to the k over 14 to the k minus 9 to the k. And the first thing that crossed my mind was like, oh, the root, the root test, because all of them are elevated to the k, but I can't take, that wouldn't work because it has a negative,
Right, because of mine,
right?
the
So
case,
like, what would it be the next thing that I should think after that? Like, how
Thanks.
should I?
you moved on to a different problem?
Sorry?
Have you moved on to a different problem? When you,
Yeah, but it was really similar, so I wanted to tie them together. That was also today. But yeah, it's a different one.
so do I see it? Well,
It's the last one, I think. The 10 of the same part.
yeah, I can make one up. I think I know exactly what you. It's number 41 in the book. We'll look at them side by side. This is page 703. So in the book, we have 2 to the k over 3 to the k minus 2 to the k. So Jenny said, she told us her thought process, and that is, let's use the root test. Everything was raised to the kth power, but Jenny also knew that the kth root of the denominator, we don't have any way to manipulate it. The kth root of a difference is not the difference of the kth roots. And so, you know, can we find that limit? Maybe, but it would have to require L'Hopital's rule. We haven't seen it before, so we can't rely on any result we know. And personally, I would rather try something else and see if we can make it work. And if we exhaust all of the other possibilities, then maybe we'll come back and look at the root test. But if we're careful, we will not have exhausted all of the possibilities. Okay, so Jenny, you gave us 2 problems. How would you like to proceed?
I think the next thing that crossed my mind was the ratio one.
Okay, are you looking at the one on the left or the one on the right?
To the right. The other, yeah.
Okay,
I mean, for the other one, I think we can use the ratio too.
yes, we can use the ratio test. And it, can I say it's pretty straightforward? Would no
Yeah.
if I said that?
Mm-hmm.
The ratio test works great. Can you tell by looking at it? For divergence?
Yes.
And so what do you think? Does it converge or diverge?
Sorry.
Just looking at the series, you get like a feeling it's going to converge or diverge. And we don't have to have a feeling for the ratio test. I'm just curious.
Converges.
Converges, yeah. So Kate, a little bit ago, you talked about the relative race to infinity of a power function versus the log function, right?
Yes.
Here we have exponential growth on the bottom, polynomial in the numerator. Well, exponentials, just like powers kill logs, exponentials kill powers. So this thing is going to converge, and there's no doubt in my mind about it. 21 is a huge exponential growth factor, greater even than the exponential growth of the COVID-19 disease. And it's just going to kill that 21st power. Ratio test works, and it will tell us that it converges. 2 exclamation points. Okay, so let's focus on, I didn't do the test, and if on the test, if I ask you to determine the behavior and justify your answer, this is not good enough, right? I would be expecting you to actually calculate the limit that the ratio test asks for and show that you get a number less than 1. I think you actually we get 120 first, but that doesn't matter. We're not doing it. Trust me, it works and it will tell us it converges. All right, so what do we do about this guy? We don't want to do the root test. We thought about it, but maybe we'll have to come back to it, but for the time being, we're not going to do it. Now, Ginny, you said something about the ratio test. You want to start, or?
Can you repeat that?
Do you want us to do the ratio test? You mentioned it, I think.
Sure. I mean, that's what I try. I don't know. I didn't know how to think through this one better. Like, if there's a better way, I should be thinking about this one. Kind of. But yeah, I mean, I guess the ratio test can work.
Let's try the ratio test. Over here, I'm 100% confident. I'm not so confident here that it's going to settle the issue. That means there's, some fun. We can figure this out. So we'll try it. 3 goes to infinity. K plus 1. So there's the K plus first term. And as you know, when our formula is a fraction, I've encouraged you to invert the kth term and skip that first step. Is that okay with everyone? Okay. Kind of a mess. These 2's that are super nice. All of these cancel, and one of these survives. So we get 2, and then we get some things that don't cancel directly because of the minus signs. You get there, Jenny?
Yes.
Yeah. So do you see anything good to try? Can you see the problem okay? Anybody have any good idea?
I was thinking, is there any way we could do like a comparison test with one that we know would be bigger but also converges?
Yeah, so Mark is suggesting that he's not liking the way this ratio test is going. And he wants to try a different test. What do you think of that, Jenny?
Well, I was thinking I can separate the 3 to the k plus. But I mean, that's not. I mean, separating 3 to the k and then 3 to the 1. And then upstairs we have 3 to the k. We just leave the 2 aside.
Yeah, with those minus signs, we can't really cancel anything.
They
Sure.
got it on the example on Pearson. This was kind of their last step, and then they just said that the limit goes to 2/3.
They just said it?
Yeah, like that was the last step, and then it was like the limit goes to 2/3, as though it was obvious.
Yeah, well, that's a pretty big step.
Yeah,
So yeah, that's when I got lost there too.
Did they use the ratio test?
yeah.
Yes.
Yeah. That's a big step. I think if I were doing it on my own, like if I were taking the test on Wednesday, I would use Mark's advice. I think I would use the limit comparison test. So let's leave this right here and we'll take Mark's advice. Hopefully, I mean, he's given us an idea, but he hasn't really given us all the details yet. And we'll see if we like it any better. So, Mark, you haven't told us what you want to compare it to.
So yeah, I wasn't thinking quite the limit comparison test, just the regular comparison test.
Yeah.
So you know how if C of n is greater than a to the n, then and C of n converges, then a of n must converge. Right? So if you get one that's bigger that we know converges, then this one would also have to converge. So I was thinking, what if it's just 2 to the k over 3 to the k? And you just completely get rid of the negative or minus 2 to the k.
Yeah, so we ignore it to come up with a good idea. We're not ignoring it in the end because we have to deal with it. It's part of the series. But yeah, it does go to 0 as k goes to infinity. So the bigger k gets, the less important that number is, 2 to the k. And if it weren't there, then we would just have a geometric series, right, Jenny?
Yeah.
2 to the k. The trouble, Mark, with the ordinary comparison is when we subtract, we make the denominator smaller, which is making the fraction
Bigger.
bigger. So term by term, these guys are bigger than the geometric series 2/3 to the k. And they could be bigger because it's converging to a bigger number, or they could be bigger because it's diverging, right? It's going to infinity. So I think it's difficult, the issue with the ordinary comparison. But Mark, your advice is super good. Let's ignore this and then let's limit compare with 2/3 to the k. So we're going to limit compare to 2/3 to the k. This piece goes to 0. Actually, it's in the denominator. So its contribution going to 0. Let's see what happens. We're going to calculate the limit as k goes to infinity. The series we know on the bottom, series we don't know on the top. And now do the algebra. Let's break this out, 2 to the k, 3 to the k. I guess I'll do nothing in the numerator. Are you with me? Those guys cancel. And by algebra, 3 to the k kicks up into the numerator. So we've simplified it a little bit. Any questions? Right.
I have a question. I was wondering what's the best way to pick, you know how you picked 2 over 3 to the k? What is your thought process when you're picking that number, like the new sum?
Oh, pragmatically, this series is so much simpler if it's not there.
Yes.
So maybe, I'll just make it simple and cross my fingers and hope it works. Now, something that confirms that choice is 3 to the k is a faster exponential growth than 2 to the k. So maybe like it's the 3 to the k term that really dominates the denominator. Yeah, we give up a little bit, but it's less and less the bigger k gets, because that 3 to the k is going to go to infinity faster. A tripling rather than a doubling rate, right? So, and
Yeah.
it's mostly like an educated guess, and we'll see if we can work it out. Sometimes it doesn't work. We do our best and we make a bad choice on the last example. I think that happened, but we got it fixed. Now, the next step is a little bit tricky. We might say, well, let's do L'Hopital's rule, but these derivatives of exponentials, the exponentials don't go away. Just, it's going to make things worse. But here's what is a super good thing to do. Let's multiply top and bottom by 3 to the minus k. I see I have 3 to the k here and here, and like, let's get rid of it. I can do it if I multiply top and bottom by something that will eliminate those. Okay? And then what happens? What do you get in the numerator? Three to the k times 3 to the minus k is
1.
1. Distribute 3 to the k times 3 to the minus k is still 1. And then we get, if you simplify it just a little bit, 2/3 to the k. Which goes to,
It goes to 0.
0. So our limit is
0.
1 over 1 minus
Oh, just 1.
1. What does that mean? Well, we're using the limit comparison. 1 means the series,
They converge or diverge together, right?
and what does this guy do?
Converges.
So they both converge. We might have been able to do something like that over here. Like, let's multiply by, let's just see if it works. It's not an obvious step, would you agree? Although look what it did. It turned this kind of a mess into not all that bad. Over here, we get the limit as k goes to infinity. By the way, we don't need to do this. We settled the issue. I'm just wondering, can we make the ratio test work? So we get 1 minus 2/3 to the k. I think maybe this is going to do the job. There's an extra 2. Let me pull that out of the limit. And then we're going to get 3 minus 2/3 to the k plus 1. Yeah. These pieces go to 0. Right? Can you see this okay? So the limit is twice 1 minus 0 over 3 minus 0. That's 1/3. That's less than 1, so it converges. We got the same conclusion both ways, so that's nice. Converges. Okay? Good
In the
call.
one to the right,
Yeah.
did you say that the other one converges? Which one did you mean?
So you mean over here?
Yes.
Yeah. So we're comparing this guy to a geometric which converges. So we're doing a comparison. We take this guy and looking at it makes us choose this.
And we found that 2/3 to the k converges, and therefore the other one has to converge. Is that what we're saying?
Yeah. It should be obvious that this one converges. You agree with me? Why? How do we
Yes.
converge this?
Because the form that it is in,
Pardon?
the form that it's in.
And what form is it?
Well, I know because I have seen it before.
What kind of a series is it?
It's a geometric series, right?
Metric. And R is 2/3, which is less than 1. So when we do a comparison test, the series whose behavior we know, that is P series or geometric series, are super important because, you know, we can choose one of those and we know without no calculation, does it converge or not? Because we're memorizing those conditions. The P series, if P is bigger than 1, the geometric, if R is between -1 and 1, it converges. So hopefully we can get that fact for free and then, you know, hopefully calculate the limit. So in the end, it took the same trick, multiplying by that. And we could have done it on the ratio test. Maybe we wasted our time going over there, since that's what we had to do in the end anyway. We could have just done it here. And Kate, there's the 2/3 you mentioned. Any other questions?
I had one more
Okey-doke,
that I would like to work on.
fire away.
It's the 10.8, number 18
Number
in the
8.
book. Yeah, he used e to that something and
Yep. 10.8.18. Summation 1 plus a over k to the k, right? K equals something to infinity. Can't be 0. 1. And they just say a is some number. So someone tell me what to do. Jenny is asking, how do we do this? So Kate or Mark, anybody have a good idea?
I guess we could use the root test, but it also looks like the form we got earlier, which had to do with exponential growth.
Correct. I think the root test will fail. Let's try it. You know, it looks like a good one with that kth power. The limit as k goes to infinity, the kth root of 1 plus a over k to the kth. The power and the root cancel directly. No subtraction. So the root behaves nicely. I get 1 plus a over k. And what's that limit, Mark? Or Jenny? Or Kate?
It would be 1 plus a.
As k goes to infinity.
Oh wait, sorry, it would just be 1.
And what does that mean for the root test? Fails. Right? Less than 1, bigger than 1, settles the issue. 1 does not settle the issue. So what's the other thing you said, Mark?
I said it looks similar to that, or almost actually exactly like the form we got a while ago that had to do with exponential growth, where it ended up being like e to the a or something.
Cover up the sigma. What is the limit of the formula that generates the terms?
It would be e to the a.
E to the a. And e to the a is not
Greater than, it's not 0, so
0. So
it should diverge.
diverge by what test?
The limit, not limit comparison. It's called the divergence test, right?
Test. Yeah, the terms do not go to 0. They go to e to the a, which is not 0. So the series diverges. Now, if you remember, when we talked about this limit in class, in all 3 sections, most of the students thought the limit was 1. That is, the fact that it converges to something involving e is not obvious. We know it because we worked it out back in Calc 1. But even if you mistakenly think the limit is 1, like most students did, the divergence test, it still settles the issue because 1 is not 0. So you can get the right answer without knowing the right limit. Now, if I ask you to justify your work, and that's what you said on the exam, I would take some points off because you're basing your results on a faulty value, right? And so it's only by luck that you would get the right answer. And we don't generally try to reward luck. We'll reward it to a degree, but not 100%.
If this was the
John-
class you teach on probability, would you still reward points for luck?
Less so.
Jen, I have a question. So I understand where E comes from 1 plus 1 over K to K, but where did you got that A? Or like that number that is in top?
Yeah, it looks like a 9. It's actually an A. This should not be an equal sign. It should be an arrow. It's a limit. It only equals that in the limit. So here's the fact that we derived in Calc 1. The limit as k goes to infinity, 1 plus any old number to the k divided by k to the power k. That limit is e to the a. So the structure tells us e, and then whatever number this is, that becomes the exponent. Okay? So that may not answer your question, Jenny. To answer your question, we maybe need to go back and derive that limit the way we did in Calc 2, using L'Hopital's rule and logs of all of that.
Okay, I kind of remember. I just didn't understand if it was a 9 of an A.
Oh.
But now it makes sense.
I tried to write it real carefully up above to make my
Yes.
like a 9. I know sometimes that happens. Any other questions? I have one more problem for you, if you don't mind hanging around for a few minutes. I saw this in the book somewhere. I'm not going to bother to find it. It's either in section 8 where there was a whole bunch of series, or it's the review section at the end. One of those, Mark, is where you found that one that we talked about earlier that was a little bit of a challenge, log k over k to 3 halves. Here it is. Let's go from 1 to infinity. 1 over the square root of n times the square root of n minus 1. Let's make it n minus 4 just for the fun of it. Yeah, that'll work. If we start at 5, so we avoid all the zeros in the denominator. So what do you think? Tell me, this is on the exam on Wednesday, let's say. What are you going to do? How are you going to process it? Let me change it just a little bit. What do you think? You got a good idea?
Will you multiply those parentheses for the square n so the squares can go away?
I just got a chat message. Okay, say it again, Jenny. I can, yes, I can do that, but it may not do everything you said. Oh, it came back. The square root.
Yeah, never mind.
So, I mean, it was a good suggestion. We have 10 ways to settle the issue, 7 tests, 2 specific series definition. What should we try? Someone give me an idea. We use the rate.
Since
Oh,
it's continuous positive and decreasing, I guess you could use the integrand test possibly. I don't know if we can figure out a way of.
integral. Yeah, in theory, but
Substitute for root n times root n minus 4.
yeah, that could possibly work, but it's a lot of work. Let's see
Yeah.
if we'll put it on reserve if we can't find anything better. Okay, this function is called an algebraic function. I mean, you can see algebraically how to calculate its values, right? We know how to do square roots, we know how to subtract 4 and so on. And it is a fact that the ratio test will never work for algebraic functions. It will always get 1. So we don't want to try the ratio test. We don't want to go through all the work and only get 1 to find out it's inconclusive. So pretend like the 4 is not there. Then what do you notice about the series?
It would be a p-series, right?
It would be, and P would be
1
1, which
diverges.
diverges. Okay? So it's kind of like a P-series. How do we turn kind of like into a test?
Comparison or limit comparison test.
Yep, let's do limit comparison. Limit comp with the harmonic series. All right, you see these guys right here, there's an n. No, there's another square root n, but hopefully limit comparison will take care of that. So we calculate the limit as n goes to infinity. The series we do not know. On top, the series we know. On the bottom, simplify. Gets me n over n minus 4 square roots of n. That's an ugly n. We can use L'Hopital's rule. So I get 1 on the top, I get 1 at the front of the bottom. The derivative of the square root of n is 1 over 2 square roots of n. What's that limit?
Just 1.
Yep. So limit comparison, we get 1. What does that mean?
It means they converge or diverge together.
Yeah.
And since the harmonic series diverges and this one diverges too.
Yeah, now step back. Can you see basically the harmonic series in there? Like square root of n, square root of n. You can, can't you?
I can almost see it. I don't know. I'm not that good yet, but
Yeah. All right. Well, Mark, you've survived to the end. Everybody else.
I do have physics at this exact time, so I got to go now. But thank you very much.
Okay, thanks for showing up, and we'll talk to you Wednesday or watch you take an exam, I guess.
See
All
you
right.
Wednesday.
Bye.